Welcome, lab rats and junior lab rats. This is just a quick little lesson to hopefully give you some helpful information on how to navigate class, as well as some information on how to navigate science in general. So welcome to Earth Science. I'm very excited about this year. We're going to do a little bit of discussion about how to science. We're going to treat it like a verb for a few minutes. So first things first, you're going to want to have your class binder and a pencil ready. If you've already picked up your binder, super. If you haven't picked it up and you're not going to be able to get it prior to having to do this lesson for class, you can go ahead and look at the online resources that have been provided for you, because what we're going to really be looking at here is how to use your syllabus and your lessons. So hopefully you'll be able to access all that online, but it would be best to have a hard copy in front of you. So if you haven't already done so, go ahead and read or skim through the syllabus and the preface section of your binder. You'll notice that your binder's pages are subdivided by section and that they're numbered accordingly within each section. So there'll be a preface section, a syllabus section, and then you'll come to your lessons. So once you have skimmed and read through the syllabus and the preface, go ahead and turn to the first page of lesson 1. Flip through the pages of lesson 1 and notice any blank space. You're going to very often have blank spaces to fill in as part of your weekly assignment. Sometimes it's going to be part of a worksheet. Sometimes it'll be what we call slotted notes, which will basically be like a traditional outline format with words missing that you're going to want to fill in. You'll fill in these blanks as you work through each week's lesson while reading or by watching a video like this one, for example. These pages will remain in your binder to help you study and prepare for tests. You're not going to want to give me any of your binder lesson pages unless I ask for them specifically for some reason. You will usually have a homework assignment to follow each week's lesson. On the final page of your lesson, right before you get to your lab, you're going to find your homework page. This page is going to show you whether your homework is to be completed through your online portal Teacherease, or if it's to be completed on paper and uploaded to the portal, or perhaps completed on paper and handed in class. This exact same information is going to be provided on your syllabus and in Teacherease. So in science, we call this sort of repetition of information redundancy. That's because if it's missed in one place, you're going to find it again in another, and that helps keep a system from failing. If you haven't already logged into Teacherease, you'll want to pause and do that right now. So one category of assignments on which you'll be graded this year is your homework and binder work. In the past, they've been divided into 2 categories. This year, they're going to be 1. So to receive credit for your binder work, I must have a reason to believe you've completed it. So how will I know that? If you're participating in class discussion, you're answering questions, you're sitting with your binder open maybe, then I have reason to believe that you're keeping up with your binder work. At any point, I can ask to see your work, or I might just stroll around class and look over your shoulder to see that it's done. This is why you also want to bring your binder to class every week. If you don't, I have no way to be sure that you're doing your work. Plus, it helps ensure that you can participate when I ask questions, because you should have most of your answers right there in front of you. Completing your binder work and your homework is a full 15% of your grade. If you want to receive the credit for the homework, you have to turn it in as instructed for each assignment on time. And that's going to be different depending on the assignment. So your homework is with 10 out of 15 points, and your binder work is worth 5 out of 15 points that you can earn in this category each week. And I'm going to award the points for each lesson. They'll be counted on the day the homework is due. And that's because typically if you're coming to class for, say, lesson 1, you should have your lesson 1 binder work complete, but your lesson 1 homework won't be due until the following week. So it will be on the date for lesson 2 that I would count the credit for both of the assignments in this category. So on the back of your weekly homework assignment page, you'll find an image of our mascot, Rico. And each week you have the opportunity to color him according to a theme and turn him in for a prize. This is completely voluntary. Some people love to do it, some people never do it. But if you have a homework assignment that needs to be completed on paper, he'll be right on the back of that paper. Otherwise, you can just hand in the sheet separately. So we're going to keep flipping, and at the very end of each lesson, after that section is over and after the homework section is over, you're going to find your weekly lab. Now, sometimes your lab is going to be turned in the following week. Sometimes you'll complete it in class and turn it in. Other times you'll just complete it in class and not turn it in. It'll be specified for each week exactly what's expected of you for lab. So now let's flip back to the first page of lesson 1. Let's have a look. So this is an example from another class I taught. This is biology here, not earth science. But if you'll notice, the syllabus entry for a lesson is repeated on the first page of that lesson. So if you look at the syllabus for lesson 1, for example, you're going to find the exact same text on the first page of lesson 1 in your binder. Again, here we are with redundancy. So to know what assignments to do each week, you can look in either place, and of course you can also always check. So now that you know what to do for class, let's go ahead and get started with some basic information on science in general.
Rico presents How to Science.
So what's science? All right, so Google defines science like this: the intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. That's a mouthful. So let's break it down just a little bit. Let's say intellectual means mental, practical means hands-on, encompassing, surrounding, systematic, organized, structure, construction, behavior, actions, physical, touchable, and natural, feel. So basically what we're doing is we're just going to replace some of those words with some more familiar words, maybe. Observation, watching, and then lastly, experiment, testing. So now our definition becomes the mental and hands-on activities surrounding the organized study of the construction and actions of the touchable and real world through watching and testing. That's better, but let's simplify it a little more and say the study of the natural world through knowledge about the natural world that is based on facts learned through observation and experiment. So science is broken down into 3 main branches. We have formal sciences, natural sciences, and social sciences. Our formal sciences consist of things like mathematics, logic, and statistics. These are things for which we can typically find exact answers. Then we have our natural sciences, and those are subdivided into physical science and life science. And life science would consist of things like botany, zoology, ecology, and genetics. Physical science would be things like physics, astronomy, chemistry, and earth science. And we'll be doing a little bit of a little bit of astronomy along with our earth science this year. It'll be earth and space. And then your social sciences are things like societies and human behavior. So what are the big ideas in earth science? Our big ideas in earth science consist of systems. Earth is a system of systems within other systems. This reminds me of Men in Black. If you've seen that movie, you know what I'm talking about. Energy. The flow of energy drives the cycling of matter. Life and the environment. Life, including human life, influences and is influenced by the environment. Unchanging drives change. So physical and chemical principles are unchanging and drive both gradual and rapid changes in the Earth system. And then modeling and mapping. To understand, have a deep understanding of time and scale of space, models and maps are necessary. So let's talk for a minute about scientific theory versus scientific law. Scientific theories versus scientific laws. Now first, you see that little thing that just spun up there in that corner? If you've been around before, you may have heard me say something like this, but now I'm going to try to use this little graphic too to help you remember. So it says engrave it for eternity, and there's Rico with a tiny little chisel there. Basically, if you see that little graphic show up on any slide, or if you hear me say those words to you, that means that this is something I want you to never forget, and it's probably going to show up on every midterm, every final, every anything of substance I ever give you. So, what is the difference when you're studying science between a theory and a law? A scientific law tells what happens, a fact. A scientific theory tells why it happens, an explanation. I promise you that if you memorize those 2 sentences exactly as they are and place them on any test where I've asked this question, you will get full credit. So, this is what's important to remember. In this class, we're going to study scientific law and scientific theory. So for example, let's take the theory of origin. There are multiple theories of origin. In this class, it's a science class, we're going to teach it from a scientific perspective, and any theories of origin discussed in this class are going to be scientific theories. So that means that even though different people hold different personal and religious beliefs, it's going to be safe to assume that all questions and answers in this class are going to be prefaced with a little unvoiced according to scientific theory rather than I personally believe that. So you can answer a question in science class giving the scientifically correct answer, and it doesn't mean that it's necessarily what you personally believe. It means that it's what science has stated as the theory. So why is measurement important? Now let's talk about measurement for a bit. Well, think about it here. There are a lot of measurements that surround you on all sides, and guess what? They matter. So in science, we are going to measure lots of things, including length, mass, which is how much matter something has. We'll talk about matter a lot this year. Weight, which is basically gravity's effect on that mass. Area, which is 2 dimensions, like the surface of a floor. Volume, which is 3 dimensions, like a liquid volume, for example. Density, which is how much mass is contained in a particular given space. Time, and temperature. Now in the US, we commonly use the imperial or standard or customary system. So this is what you're used to. Inches, yards, cups, tablespoons, gallons. When you go to the store, you buy a gallon of milk, right? But in science and in most other countries in the world, the metric system is what's most often used. And this consists of base units like grams and liters and meters. And then it also has these wonderful little base 10 units that make it so much easier to convert than when you're using the system we use here in the US. So here's what I mean. Metric conversion. We're going to say in the center here, we have meter, which is length, liter, which is liquid volume, and gram, which is mass or weight. And if you multiply by 10, going from the left to the right, you're getting smaller. And if you go the opposite direction from the right to the left, you're dividing by 10 and you're getting bigger. So basically, if you look on the far left there, you've got kilo. Well, 1 kilo is 1,000 units. So if your unit is a meter, 1 kilometer is 1,000 meters. And on the opposite end, we have milli or milli. So this is going to be 1,000 times smaller. So it's a 1,000th of whatever your unit was, or 1,000 milli units equals 1 unit. So basically, we'll be using it a lot this year, but you'll hear words like kilometer, centimeter, milligram, gram, and this is what we're talking about. And there's a nice little mnemonic there. It's King Henry died unusually drinking chocolate milk. Sometimes people used to say Monday because they're always putting meter in there, but that doesn't work if you're using liter or gram. So if you can remember unusually, that stands for unit. And if you haven't seen this before, you'll get used to it pretty quick. So how do you present scientific data? Well, there's lots of ways to present scientific data. So data are information gained from observing and testing an experiment. Now, data is actually your plural. Datum is your singular, but you don't use it very much because usually you're collecting multiple points of information. So it's usually data. So scientists use data to gain understanding and make conclusions. Now, at the bottom there's a little bit about scientific notation. This is when you're using really, really, really big numbers, or really, 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 really small numbers. And when we get to it, we'll practice it some more if you haven't done it in the past, but it actually just basically has to do with moving a decimal and counting. So it's not maybe not as scary as it might look if it's new to you. So there are lots of other ways you can present data, charts and maps, and we'll be using a lot of maps this year. So what's a hypothesis? Okay, now a hypothesis is an idea that can be tested. Now, I want you to watch closely here. Requirements for a testable hypothesis. In order for a hypothesis to be considered testable, it must be possible to prove that the hypothesis is supported, you might think true, or prove that it is rejected, not true. And it must be possible to reproduce the results of the hypothesis. Now, what popped up in the left-hand corner? There you are, engrave it for eternity. So in order for a hypothesis to be tested, and remember, a hypothesis is an idea that can be tested. So in order for your idea to be testable, you have to be able to prove that it is supported or rejected. And in either case, you have to be able to reproduce those results. So many scientific hypotheses, there's your plural of hypothesis, are proposed in an if-then format because it's easy to design an experiment to see whether or not a cause and effect relationship exists. between the independent or manipulated variable and the dependent or responding variable. So we'll get back to variables in just a minute. So what if your hypothesis is supported? A scientist will make sure that she can repeat her process and replicate her results. And what if it's not supported? What if it's rejected? Then a scientist will revise his hypothesis and often repeat the experiment. So what's scientific method? So scientific method is a way of going about this testing. So it's how we conduct what we call a controlled experiment. Now, as you can see from this flowchart, it's not a straight line. There are lots of turns you can make. And that's because there is no one specific straight way to do a controlled experiment, but there are some things you do have to keep in mind. And these are the three big ones. Your independent variable, which is what you change, your dependent variable, which is what you observe, or your controlled variable, which is what you keep the same. So in a controlled experiment, it's an experiment in which only one variable, the independent variable, is deliberately changed at a time. And there's the little engrave it for eternity thing. And this is because you're going to want to remember this independent, dependent, and controlled bit. Because if you change too many things in your experiment and then your results at the end are different, how will you know what caused the change? You won't. So a controlled experiment is when you keep everything the same except for the one thing you're going to change. So how do you be a good scientist? So a good scientist engages in arguments using evidence. This is important. Evidence, not emotion or feelings or thought or belief, evidence. A good scientist asks questions and defines problems, develops and uses models. This helps people conceptualize what it is you're talking about. Plans and carries out investigations, analyzes and interprets data. That's very important. Analyzing and interpreting data doesn't mean that you take the data at face value as someone explains it to you. It means you analyze and interpret it yourself. He uses math and computational thinking, constructs explanations and designs solutions, obtains, evaluates, and communicates information. Be a good scientist. So here are some good scientists just to wrap this up. So Rachel Carlson here at the top, she said, one way to open your eyes is to ask yourself, what if I had never seen this before? What if I knew I would never see it again? And Rachel Carson's work increased understanding of the environmental dangers of certain chemicals, such as DDT in particular. Edwin Grant Conklin over here next to her said, life is not found in atoms or molecules or genes as such, but in organization, not in symbiosis, which is how things work together, sort of in a way, but in synthesis, which is a similar word, but not exactly the same. It's kind of what things create when they're working together. And this is a guy who pioneered the fields of what we call cellular lineage in embryology. So it has a lot to do with DNA and DNA's evolution over time. Then we have Darwin at the bottom. It's not the strongest of the species that survives, nor the most intelligent that survives. It is the one that is most adaptable to change. A lot of people like to credit Darwin and his theory of natural selection with the concept of survival of the fittest, but what he meant by fittest wasn't the strongest or most intelligent. It was the one that was most adaptable to change. And he actually had a hobby of breeding fancy pigeons, which is my favorite Darwin fact. And then Marie Curie here at the bottom, who is one of my favorite ever, she said, I'm among those who think that science has great beauty. A scientist in his laboratory is not only a technician, he's also a child placed before natural phenomena which impress him like a fairy tale. And she's known for the discovery and work with radioactive elements that aided in cancer treatment. So science, is it settled? As we're wrapping up our lesson, let's remember, lastly, never forget, no matter who says otherwise, science is never settled. Why is this a wrong-headed assertion? All right, one, oh, there he is. One, it presumes science exists in a binary state. It's either off or it's on, it's right or it's wrong. That science isn't settled until it crosses an imaginary line after which it's finally settled. On the contrary, science is, by its very nature, never 100% settled. 100% is when we're talking about formal sciences. We'll come back to that in a second when we get to point 3. Number 2, it presumes that poor understanding in one area of science invalidates good understanding in other areas of science. This is not the case. A good example would be this. If you've ever undergone anesthesia, scientists know that anesthesia works because they use it in, for surgery and stuff, but they don't honestly understand down to the nitty-gritty exactly how it works. So they may have a little bit of a poor understanding of exactly how that works, but they do know how to go about taking out your appendix. So that's good understanding in one area and poor understanding in another. Doesn't mean that one invalidates the other or means the other isn't true. And lastly, natural science is not about absolute proofs. This is the big one. It never reaches 100% certainty. This is the domain of the formal sciences, mathematics and logic. Science is about improving our understanding and by narrowing uncertainty. That's a big one. Remember that. Different areas of science are and likely always will be understood with varying degrees of confidence. So you could ask these guys because these are some people who proved that science wasn't settled. Galileo Galilei proved the sun was at the center of the solar system, not Earth. Before that, everybody believed it was Earth. Darwin introduced the worth of the theory of natural selection, providing the first explanation to the idea of evolution. We'd seen evolution in, actually occurring before our eyes. You can see it happen in microevolution in small populations, but nobody understood how it worked. He is the one. Joseph Lister applied germ theory to create the concept of sterile surgery. Thank goodness for him. And if you didn't know about Lister, the product Listerine is named after him, for one thing. And then Alfred Venegar. This is the guy who originated the theory of continental drift, which actually proved to a great many people that the Earth is in constant movement and is constantly changing, which we will be talking about a lot this year. And then here, Robert Goddard, he was laughed at when he suggested that we could use rockets to travel to space, which is kind of funny considering it happens all the time now. So who's going to make the next great discovery? You never know, it could be you.